All right, today what we will do is we will start a brief introduction on the periodic table. We will start to explore ions and how these ions are formed, and then we'll also start to discuss chemical formulas. So let's go ahead and start by thinking about chemical symbols and then some elements on the periodic table. So whenever we look at the periodic table, what we'll see is that there are 118 elements that make up the periodic table. They can be named after someone that's discovered elements, or they might be named in tribute of a scientist, but many times it's named after their properties. And these names tend to have Greek, Latin, or Arabic roots. Out of these elements, these 118 elements, there are millions of known compounds. And really, there's probably about 40 to 50 elements that make up the majority of these compounds. But there's millions and millions of compounds that are either formed naturally or synthesized in a laboratory setting. So this is quite incredible as you start to think about it. Let's go ahead and talk a little bit about the periodic table and the symbols that are used. Some of the symbols are derived from their name. So if we think about the element oxygen, the chemical symbol for that is an O, or for aluminum, it's Al. So all of these make sense. Some of them might not make as much sense to us, but whenever we look at the original language that these elements have roots in, they would make more sense. So iron is Fe, but then the Latin root for ferric or ferrous, depending on the charge on the iron, that would have Latin roots. So we will talk about the arrangement of the atoms on the periodic table and properties later, but right now what we really want to do is focus on being able to find the elements on the periodic table and some of the information that's given on the periodic table, and start to get an insight as to what types of ions these elements actually form. So as we start our introduction to the periodic table, I just want to briefly mention that the periodic table is arranged in the following way. It follows a periodic law. So what we mean by a periodic law is that the properties repeat themselves. Okay, so the periodic table is arranged in kind of two basic ways. One way is that it's arranged in increasing number of protons, or as the atomic number is increasing. The other way that it's arranged is periodic law, and we try to align things vertically in columns with how they tend to interact, or their reactive properties. So whenever we talk about the periodic table, we either talk about periods or groups. So periods are the rows, and then the groups are the columns. So I just told you that we arrange things in columns by their reactivities, or what properties they have. So we would call that a group. Okay, and we'll explore some of the different groups here in just a little bit. And then the rows are periods. So I usually use this right here to remember which way groups and periods go. So we have groups, that's vertical, and then periods are horizontal. The other way that things are grouped together on the periodic table are in terms of metals, metalloids, and nonmetals. So let's go ahead and start talking about metals. So metals are good conductors, okay? And whenever we talk about good conductors, we are talking about of heat and electricity. And this is just a general property. And then for nonmetals, they tend to be poor conductors. And we'll see how these are arranged on the periodic table in just a minute. So then metalloids, they kind of are intermediate between those of metals and nonmetals. So they have properties that aren't quite metallic in nature, but not quite nonmetals either. So let's go ahead and look at a periodic table. And this can be found in the OpenStax textbook, or really any chemistry textbook at that. But let's go ahead and look at some of the different groups, because we will need to navigate our way around the periodic table and learn what we'll call the geography of the periodic table. So we will need to know what groups 1 and groups 2 are. So group 1 are the alkali earth metals, and then group 2 are the alkaline earth metals. So the way that I remember group 1 and group 2 is that if you arranged alkali and then alkaline in alphabetical order, it would be alkali would be first and then alkaline would be second. This whole middle part of the periodic table, which we'll learn another name for eventually, these are called the transition metals. So we have metals over here in the alkali and alkaline earth metals. And then as we start to go right across the periodic table, from groups 1 and 2 all the way over to 15, 16, 17, and 18. So over here, this side of the periodic table, these tend to be non-metals. Okay, and group 18 are noble gases, and gases are definitely not metals. You'll need to know this group 18, you'll need to know group 17 and 16 and 15. Okay, so and then what we'll know is that for the halogens, for example, fluorine is the halogen that's highest on the periodic table. It will have similar properties to that of chlorine and bromine and iodine. And then for the chalcogens, that would be looking at something like oxygen is the highest chalcogen on the periodic table, and sulfur, and so on and so forth. And then the nitrogens would be nitrogen. The other thing on the periodic table that sometimes we'll refer to, we'll talk about these properties a lot more later, but these are the lanthanides and the actinides, or the lanthanide stretch and the actinide stretch. And these kind of slide in here in the lower 2 rows in the transition metals. But you can recognize which ones are the lanthanides and which ones are the actinides, because the first element in this particular group is lanthanum, and then this first element is actinium. Okay, so we might come back to this table and start to assign some different charges to groups that they tend to take on, or at least reference these groups shortly. So the next thing that we want to do is try to figure out, how do we represent charged atoms or compounds, or what we would call an ion. Okay, so we've already talked about a neutral species, and here we had the mass number and then the atomic number. Now, as we're starting to deal with charged atoms, this here, the script delta, this is going to tell us what the charge is, and will indicate whether it's positive or negative. So for instance, let's say that we had sodium 23, okay, so, and then with a +1 charge. So we would just put a plus. Okay, if there is no charge indicated, okay, so if there's nothing there, if that's not present, then that just means charge is 0. There's no charge. Okay, so this tells us the charge. And then the subscript here on the right hand side, this tells us the number of atoms present. So we're starting to talk about molecules then. So just to recall, A is your mass number, and Z is actually redundant to X, but then that is your atomic number. That's your number of protons. Okay, so right down here I wrote sodium 23, and it has a +1 charge. Okay, so that is what we would call a cation. And a cation, by definition, is an ion with a net positive charge. So if you have a net positive charge, that means you lost an electron, because recall that electrons are negatively charged. So let's go ahead and compare sodium 23 to the sodium 23 cation. So let's think about the protons, the electrons, and the neutrons. So both of these have 11 protons because they're sodium. For the neutral version of sodium, we would have 11 electrons to balance out the charge. And since the mass number is 23, we would have 12 neutrons. Okay, now that over here for the sodium 23 cation, since there's a positive charge, it would have lost an electron, so now there's only 10 electrons, and then there are 12 neutrons. So this is an example of a cation. Okay, well, let's consider an example of maybe chlorine 35 versus chlorine 35 with a minus charge. So this is what we would call an anion. So the anion can be described as an ion with a net negative charge. And then this is a species that has gained electrons. Okay, so if we look at chlorine, chlorine has an atomic number of 17. Both of these would have 17 protons. Since they're both chlorine 35, they would both have 18 neutrons. The neutral chlorine 35 would have 17 electrons, whereas the negatively charged chlorine, that anion, would have 18 electrons. Okay, and then we can also have species that have more than a plus or minus 1 charge. So let's look at oxygen 16 versus oxygen 16 with a 2 minus charge. So both oxygens would have 8 protons. The neutral oxygen would have 8 electrons, 8 neutrons, whereas this anion would have 10 electrons and 8 neutrons. One of the easy ways to remember that a cation is positive, if you start to consider how cation is spelled, you can actually see that there's a positive charge right there. All right, so let's go ahead and skip ahead to some chemical formulas really quick and talk about these. So a chemical formula is just going to start to combine different atoms together to show what compound is being formed. So it tells us what atoms are, or what elements are present and in what ratio they are present in. So we have to be really mindful of subscripts versus coefficients. So if we have H2O, that's looking at a single water molecule. Okay, if we have two H2Os, well, now we're starting to talk about there being 2 water molecules. And you don't have to know how to draw this just yet. We'll go over Lewis structures later this semester. And then finally, if we have H2O2, that means something entirely different. That means that this is hydrogen peroxide. So whether we have a coefficient or a subscript really tells us something about how many molecules there are or what the ratio is within that molecule. So remember that subscripts will tell you how many atoms are in a molecule. Whereas a coefficient tells you how many molecules. We won't worry so much about this notation, but for organic compounds, instead of writing this formula down here as C2H4O2, it's written out as CH3COOH because that tells us how these atoms are bonded together. And we will learn how to decipher this at a later date. So there's a few more things we need to realize about formulas. So a molecular formula is written in the ratio that they exist in. So for instance, if we take that molecule from the last slide, we have C2H4O2. That tells us exactly that there are 2 carbon atoms, there are 4 hydrogens, and 2 oxygens in this molecule. Okay, but if you are given an empirical formula, this is going to tell you the simplest ratio. Okay, so in this case, we could go through and divide by 2. So the simplest ratio of this would be CH2O. So this is what we would call the empirical formula, and sometimes I will abbreviate that as EF. And then the molecular formula up here is C2H4O2. Okay, one other thing that we should take note of is every now and then we'll see an allotrope. And this would describe one of 2 or more distinct forms of an element. So for example, if we had O2 versus O3. So if we're looking at oxygen versus ozone. So let's go ahead and consider hydrogen peroxide again. So hydrogen peroxide has a molecular formula of H2O2. And we can simplify that to have the empirical formula of just HO. So before we start exploring ionic compounds, we need to consider the cations and anions and what kind of charge a single atom or a group of atoms would take on. So whenever we start talking about ions, recall that that was looking at the loss or gain of electrons. If we are looking at a single atom, we talk about that as being a monatomic ion, and that charge is equal to the oxidation number, which we'll define here shortly. So if it has a positive charge, it has a positive oxidation number. If it has a negative charge, then it has a negative oxidation number. But sometimes what we'll see is we'll have polyatomic ions. And polyatomic ions are going to be an ion where there are more than one. Okay, so 2 or more atoms are making up an ion. So this OH minus, and we'll learn that this is called a hydroxide ion. So the negative charge is on this entire ion. So what we'll see is that whenever we start to have an interaction between a positive ion and then a negative ion, okay, we're going to call this interaction, this isn't a smiley face, this is what we would call an ionic compound. Okay, so let's look at these compounds and have a really quick inspection of these. So the first compound we want to look at is going to be one that's formed from a sodium ion and a chloride ion. So one of the things that you should note is that the alkali earth metals, so everything in group 1, they are going to tend to take on a +1 charge, whereas the halogens in group 17 will tend to take on a -1 charge. So what we want to do is try to figure out how are these ions going to combine in a ratio such that the overall charge is 0. So we want to determine the ratio, and we want the overall charge to be 0. Okay, so this is a simple example because both of these have the same magnitude of the charge. This is a +1, this is a -1. So it's the same magnitude but opposite sign. So what that means is they're going to combine in a 1-to-1 ratio. So that means that we will form the compound NaCl, which is sodium chloride. Okay, so now we need to ask ourselves, what happens when the cation and the anion do not have the same order of magnitude? Well, let's go ahead, and what we want to do now is we need to have a strategy for quickly determining the ratio in which ions combine, but still keep the overall charge as 0 where it's applicable. Okay, so what we always want to do for these ionic compounds is we always want to list the cation first and the anion second. So in this case we have calcium 2+. So calcium is in group 2, and that is an alkaline earth metal, and that group tends to have a charge of +2. Bromide, so Br-, this ion is a halogen, so it has a -1 charge. So what ratio will these combine in? So we need to get the overall charge to 0. So since calcium has a 2+ charge and bromide has a -1 charge, we're going to end up having our compound be CaBr2. Or another way to look at this is if we consider calcium 2+, Br-, what we can do is a quick and simple method. We call this swap, drop, and multiply. So we swap and drop the charges. So we end up with Ca, and then since bromide has a -1 charge, we just take the magnitude. So we have Ca, and then Br, since calcium has a 2+ charge, we just keep the 2 with the Br. Okay, and then we'll have to look at an example where we do have to swap, drop, and simplify in just a second. Let's go ahead and look at aluminum and hydroxide. So if we look on the periodic table, aluminum is going to be in group 13 or group 3A. So aluminum is going to take on a 3+ charge. And then I told you that the polyatomic ion of hydroxide will have a -1 charge. So what we'll see is that we will need 3 hydroxides for every 1 aluminum. But you need to make sure you keep your hydroxide in parentheses and then you put the 3 on the outside. So that tells everyone that you need 3 total hydroxides. Okay, and this would be another example if you wanted to swap and drop. Just make sure you have polyatomic ions in parentheses so you can distribute that subscript like it's supposed to be. So if we drop the 3, drop the 1, again we end up with AlOH3. Okay, well, let's consider an example now that we need to simplify. So consider if we have magnesium 2+ and oxygen 2-, so we want to see how these combine. Well, these have the same charge, so we might think, okay, if we swap, drop, and multiply, or simplify, excuse me, we would have Mg2O2. Okay, but we can simplify that. So it should actually be MgO. Okay, so if you do this swap, drop, and simplify, make sure if you have 2 of the same subscripts that you're going to simplify that as much as possible. But probably just as easy of a way is to look at it and say, well, magnesium has a 2+ charge, oxygen has a 2- charge. So these ions are going to combine in a 1-to-1 ratio. Okay, so that does it on this discussion where we explored the initial setup of the periodic table, ions, and how ionic compounds are formed, and then different chemical formulas. Next time we're going to learn how to start to name these compounds.